This one here is usually just called the trivial group, and it's sort of smaller. Its order is smaller than the group itself. Okay, it's sort of in the middle-sized. So it's bigger than the trivial group, and it's smaller than the group itself. Okay, so that's called a proper or non-trivial subgroup. Can we find some non-trivial or proper subgroups in this group, this group here? Well, this one, the subset IRS, it's a group. It's obviously smaller than the big one. It's obviously bigger than just the trivial group I with only the unit in it. Okay, so there's an example. Are there any others? It works out like I and X is sort of obvious. Like here's the operation X, and if you do it twice, that's doing it once, and you do it again, you go, you get back to where you started. So X squared. So in other words, X by X, and it'll just give you the unit. Okay? And so this set here of the unit and X, so these two operators, they're actually a group, very small one, just order 2, because 2 elements. Okay, so this set here is actually a group, of order 2, because 2 elements. And similarly, similar logic. The reasoning behind why I and X is a subgroup, that also applies to the I and Y. So if you do Y twice, there is once, and again, I can't do it, gives you I. Okay, and a similar logic for Z. So do Z once, you get that, and do it again, well, you just end up with what you started with. All right. Now, how about this one? Is IR a subgroup? Well, firstly, if it's not even a group, it can't be a subgroup, right? Then it would just be a subset. It's obviously a subset, right? I know, it's just 2 elements of this set of 6 elements. So it's obviously a subset, but is it a group? Right? So you take these 2 elements and I and R. Now, one of the properties of being a group is closure, right? So you take any 2 elements of your group, and closure implies that the product, in a sense, A binary operator B also belongs to the group. That's the condition of closure. That's the definition of closure. All right. Well, let's do RR. I mean, A and B don't have to be different. Just for all possible combinations. So if your order of your group is n, say little n, then how many possible pairs or products, A, B, do you have? Well, it'll be n squared. Okay, so all possible pairs. So here, the order of your potential group, at the moment just the set. Let's try like RR. Well, if you do R twice, that's rotating 120 degrees twice. That gives you 240 degrees. But that's what S is. So RR is S. But look, S is not in this group or in this set, right? So it's not closed. And if it's not closed, it's not a group. So if it's not a group, it can't be a subgroup, right? So this set here is not a subgroup because it's not even a group. Okay. Now let's do some examples of some groups and subgroups. So this little star here, or asterisk, I've mentioned this several times now, so you're probably quite familiar with it. This set here is the non-zero. That's what the little star means. If you see anything with a star on it, like here, here, and so on, it just means that the 0 element has been thrown out, right? There's no 0 element in that set. Okay, So the non-zero rational numbers, we talked about that a lot, so I won't go into it, and the binary operator is multiply. So here's your usual, here's your set S, and here's the binary operator, like a little circle. But here we have a concrete example of a set. It's the non-zero or starred non-zero rationals, and the binary operator is multiply. Now, can you see that H is a subgroup of G, and the set is the positive rationals, and again the binary operator is multiply. Oh, one thing I should point out, I didn't emphasize that's important. Your subgroup inherits the same binary operator as the group. So if this is your group, you've got a set G, you've got a binary operator little circle, whatever it is, plus, minus, whatever, right? Very general. Is an abstract concept, the binary operator. Then if H is a subgroup of this group and the binary operator, the subgroups operator is the same, right? It's sort of like the group is the parent, and the child. This is sort of like the child. The subgroup inherits the same binary operator. So this is the same as that. That's important. If that's not the case, then you might have a set that's actually a group for a different binary operator, but then it's not a subgroup of this, right? The two operators here and here have to be the same. Okay, that's important. All right. Okay, so why is this H a subgroup of this G? So this is all the non-zero rationals, and this is all the positive. That's what this plus here means. It's the positive rationals. Okay? Now you can now Q plus is obviously a subset of Q star. Right? I mean, like you have all the positive rationals. You have zero, and then you have all the negative rationals. Now you take the zero and you throw it out, so that leaves you the negative rationals and the positive rationals, and a break here at zero. Now the positive rationals, these are positive rationals, let's say here, that's obviously a subset of the whole thing. Right? But you can readily prove that this is a group as well. Okay, so H, this set is a subset of this. Okay, and that's a group, and you can readily prove that this is also a group. And since it's also a subset, therefore this H is a subgroup of that. And in fact, let me ask you, can you see intuitively that the size of this subgroup, in a manner of speaking, because both of these are infinite groups, but in an intuitive manner of speaking, can you see that this is half the size of that one? Now, if you've studied any kind of transfinite numbers, the sort of work that the famous Cantor, French? Cantor, not sure. French, German? Anyway, European. In the 1800s, he worked on this, mapping sets to a set of integers and countable numbers and LF0 and LF1 and all that stuff. You probably object to what I've just said, but intuitively, in a sense, the size of this one is sort of half of that one. All right. Okay. Now, what about this one? I've crossed it out, so you know already it's not a subgroup, but why not? Okay. So here's your group. It's just the set of all rationals, including zero. Okay? This one is not starred like the way that one is. So this is just all the rationals, including zero. And the binary operation is plus, and you're given a subset H, and it consists of the non-zero rationals. Okay. And the binary operation is the same. I mean, if these two are not the same, then there's no question, there's just no possibility that this H could be a subgroup, right? It's what I was just saying before. If you have a subgroup, it inherits, it gets the same binary operator from the parent group, from G. Okay. All right. So why is this subgroup H this subset? Sorry. Why is this subset H